Imagine a world where machines do more than emit and receive waves, a world where they perceive. Electromagnetic cognition is the ability of a system to sense, interpret, and dynamically adapt its electromagnetic behavior. Through waveform diversity and adaptive radiation patterns using reconfigurable antenna arrays, such systems interact intelligently with their surroundings. But this isn't science fiction, it's a new frontier at the intersection of physics, information science, and artificial intelligence. It opens pathways towards smart wireless communication, adaptive radar systems, cognitive imaging, and autonomous control. These systems don't just detect, they learn, they respond, and they evolve with their environment. This concept, like many revolutionary ideas, finds its roots in nature. Consider the bat. It doesn't blindly emit sound, it cognitively adjusts the frequency of its signal based on the echo it receives. This biological radar fine-tunes its transmissions to adapt to motion, obstacles, and target shape, a real-time feedback loop of wave adaptation. Similarly, an electromagnetic cognitive system must reform its waveforms based on the feedback it gathers. This is where geometry, electromagnetic field dynamics, and information theory intersect. By continuously reshaping its signal to respond to its environment, such a system turns passive reception into active understanding. Now, let's explore a real-world implementation, the cognitive imaging radar. This system embodies all the layers of cognitive EM functionality. Just like a brain interprets stimuli and acts upon them, this radar maps biological cognitive functions into an engineered electromagnetic system. Its architecture includes adaptive components in both the transmitter and receiver. At the heart lies a knowledge-augmented processor that links perception to action. This processor integrates sensor data, interprets electromagnetic patterns, and drives decisions about waveform shaping and beam direction. In doing so, it transforms traditional radar into a thinking, evolving machine, capable not only of imaging but of understanding what it sees. One of the pillars of electromagnetic cognition is waveform diversity. In conventional systems, a fixed waveform is used regardless of context. But in a cognitive EM system, waveforms become adaptive languages, tools to probe the environment in different ways depending on what is sensed. Think of it like musical improvisation. The system selects different notes, frequencies, shapes, pulse widths, and listens carefully to the echoes. Then, based on what it hears, it plays a new note. This closed-loop strategy enables real-time decisions about how to interact with a dynamic world. It's not just data collection, it's intelligent exploration through electromagnetic conversation. Now let's look at spatial adaptability, specifically through reconfigurable beamforming. Beamforming allows electromagnetic systems to steer their energy in specific directions. But in cognitive systems, this beam isn't fixed, it adapts in real time, scanning the environment, focusing on regions of interest, and even avoiding obstacles or interference. It's like having a flashlight that not only moves but also changes shape, sharpens its focus, or widens depending on what's in front of it. This spatiotemporal control makes the system aware of space, not just time and frequency, a crucial step towards situational awareness. One of the most compelling applications of electromagnetic cognition lies in microwave brain imaging. Here, we tackle an inverse problem, reconstructing internal structures from external EM signals. It's not a simple measurement, but a process involving data flow, control flow, and most importantly, information flow. This triad transforms the imaging system into an explorer, constantly adapting its waveforms, scanning geometry, and updating models of what lies beneath. The goal isn't just to see through tissue, but to understand what patterns mean, to extract hidden information from complex, noisy environments. This is where cognitive EM becomes a powerful tool in medical diagnostics, such as detecting hemorrhages or strokes. Finally, let's dream a little. Have you ever imagined putting on an invisibility cloak, like in the realm of fantasy? What if I told you that electromagnetic cognition might one day bring that vision closer to reality? Scientists are developing materials, called metamaterials, that control how light bends, flows, and is absorbed. With the right structure, these materials can guide electromagnetic waves around an object, rendering it effectively invisible. This isn't just magic, it's advanced physics, guided by our growing understanding of wave manipulation. These cloaking principles could revolutionize not only stealth technology but also secure communication, wave shielding, and non-invasive imaging. We are entering an age where electromagnetic waves don't just carry information, they sense, they adapt, and they think. And with them, a new intelligence is emerging, one made not of neurons, but of fields, patterns, and light.